Welcome to Kognito Key. In today's explainer, we're diving straight into the brilliant physics of step-index fiber. You know, if you've ever wondered exactly how light travels through those tiny optical cables to safely deliver all that data right to your screens, you are in the exact right place. So let's just dive right into it.
So, a step-index fiber is basically at its core an optical waveguide. But why do we call it a step-index? Well, it all comes down to how it controls the light. The fiber has this central core with a constant refractive index, and it's wrapped in an outer protective layer we call the cladding, which has a completely different constant refractive index. And that word step, it literally refers to the sudden, abrupt jump in the refractive index right at the exact boundary where the core meets the cladding. There's no gradual fade here, it is just an immediate, sharp step.
Now, for this whole optical setup to actually work, there is a very strict mathematical rule we have to follow. The core's refractive index absolutely must always be slightly higher than the cladding's. That unyielding physical rule is literally the secret sauce that sets the stage for all the magic happening inside the fiber.
Okay, so how does the light actually move? As light travels through this fiber, it follows a zigzag path. But what's really amazing is that these zigzags are made entirely of perfectly straight lines. Because of that sharp step in the refractive index we just talked about, the light ray hits the boundary and perfectly bounces via total internal reflection. It just reflects completely back into the core, over and over again, moving forward without ever leaking out. And this foundational principle actually branches off into two completely distinct physical categories: step-index single-mode fiber and step-index multimode fiber. The physics of how the light reflects is exactly the same for both, but they differ dramatically based on one absolutely crucial characteristic, and that is their physical size. Just imagine a diameter of only 2 to 15 micrometers. Seriously, to put that unimaginably tiny scale into perspective, a single strand of human hair is roughly 70 micrometers thick. So, this incredibly microscopic measurement represents the extremely narrow core size of a single-mode fiber. Because the core is just that exceptionally narrow, only a single mode, literally a single light ray, can physically fit and travel through it. And this gives us a massive technical advantage. With only one ray of light traveling down the path, there is absolutely zero distortion from delay differences. The signal you send in is perfectly maintained, and it arrives at the other end without getting scrambled at all. But now, let's contrast that incredibly tiny core with a massive jump in size. 50 to 1,000 micrometers. This much wider diameter defines our second category, the step-index multimode fiber. Because it is so much wider, it allows for entirely different mechanics inside the cable.
With all this extra core space, multiple modes, or several different light rays, can enter and just bounce through the fiber simultaneously, and these are typically powered by highly accessible LEDs. But, this creates a really unique physical challenge. Because multiple rays are bouncing at different angles, it's kind of like runners on a track taking different lanes. Some just have to travel a longer physical distance than others. And that leads to distortion, because the different rays arrive at the end at slightly different times, which is a phenomenon we call propagation delay.
Taking a step back to look at the big picture here, why is this specific technology so widely used by engineers? Well, the advantages are just incredibly practical. Compared to those super complex graded designs, these step-index fibers are wonderfully straightforward to manufacture, which makes them highly inexpensive to produce at scale. Plus, they offer remarkably reliable propagation. They just simply work, and they do it really cost-effectively.
However, to really thoroughly understand the tech, we have to look at the limitations too. First off, think back to that tiny 2 to 15 micrometer core of the single-mode fiber. Trying to perfectly align and couple a light source into a target that impossibly small is just highly difficult, and it requires some seriously expensive precision equipment. Secondly, while sending one single ray at a time prevents the distortion we talked about, it inherently limits the overall volume of information carrying capacity you have at any given moment.
So, considering all these pros and cons, where do we actually use this stuff? Because of its specific information transmitting capacity compared to those more expensive graded index fibers, it perfectly finds its home powering our local area networks or LANs. For connecting computers, servers, and devices within a localized environment like an office building, the cost-to-performance ratio of step-index fiber is just an absolute winner. Which brings us to a truly fascinating engineering question to leave you with today.
As our global data demands just keep growing exponentially, how will the physical limits of step-index fiber shape the future of our local networks? Are we going to find clever new ways to stretch its capabilities? Thank you so much for watching. Please subscribe to the Kognito Key channel and like and share this explainer.